Hello, everyone. Can you hear me? Um, I'll just
Yes,
ask maybe Dr. Sherman to confirm.
yes, we can hear you. I can hear
Okay.
you.
Okay. So I think we have people that are still calling in. Welcome to everyone who are already connected. So if we can wait 2 or 3 more minutes for others to join in, especially some of our lead partners who have confirmed, that will be great. So if you can just hold on a bit, and we will begin shortly. Okay, I think we can begin the webinar now. Hello, everyone. Welcome to the CCAC webinar titled Secondary Loop Mobile Air Conditioning Project Final Results and Path Forward. This webinar is being organized by the Climate and Clean Air Coalition, or CCAC Secretariat. My name is Denise Yoson. I am the coordinator of the HFC initiative in the CCAC Secretariat. And I will now give you a short introduction about this webinar and the project that will be presented. The Climate and Clean Air Coalition is a voluntary partnership of governments, intergovernmental organizations, businesses, scientific institutions, and other civil society organizations committed to improving air quality and protecting the climate through actions to reduce short lived climate pollutants such as black carbon, methane, tropospheric ozone, and hydrofluorocarbons, or HFCs. One of the 12 initiatives of the coalition is the HFC initiative, which has supported activities and projects to promote climate friendly alternatives and technologies since 2012. One of the work streams of the HFC initiative has a focus on technology demonstration projects, which aim to test and validate technologies that may be commercially viable alternatives to high global warming potential HFCs. And the technology demonstration of low global warming potential high efficiency mobile air conditioning project was implemented by the IGSD, or Institute of Governance and Sustainable Development, in collaboration with the automobile manufacturer Tata Motors, that is based in India, and the technology system supplier MAHLE, based in Germany. Now, our webinar for today will be for 1 hour, and we'll begin with a presentation by our panelists from IGSD, Dr. Nancy Sherman, and MAHLE, Mr. Timothy Craig, and Mr. Saurabh Chaudhuri, followed by a question and answer segment. At the end of the presentation, you may ask a question by raising your hand using the GoToWebinar software or by typing your question in the chat box. This webinar is being recorded and will be available in the CCAC website afterwards. So now I would like to give the floor to Dr. Sherman from IGSD, the Director for Technical Assessment. Dr.
Thank you,
Sherman?
Denise. Thank you, Denise. Thank you for the introduction and welcome everyone. We are delighted to be talking about our secondary loop mobile air conditioning project. I'd like to introduce my co-presenters, Timothy Craig. He's head of thermal pre-development in advanced engineering at MAHLE Behr Troy in Lockport, New York. And Dr. Surav Charuri, he's the senior product engineer also at MAHLE. The third partner in this project who isn't here is Tata Motors Limited, as Denise said. They aren't able to join us today, but they're well represented in the slides. MAHLE is a leading global supplier to the automotive industry and an industry development partner. Tata Motors is a 45 billion global organization and the largest automobile manufacturer in India. And we'd especially like to thank the CCAC for making this cutting-edge project possible by providing the funding. Okay, so many of you have seen this slide. It's the slide of surface temperature change by Velders, using data from Velders et al. From 2015. And it shows how the Kigali Amendment will phase down HFCs and prevent the business as usual scenario from happening. And the business as usual scenario without the HFC phase down is in red, with a maximum temperature change of 0.5 degrees Celsius caused by HFCs. And by phasing down HFCs, much of that will be avoided by the year 2100. The not so good news is that mobile air conditioning is a very large contributor to climate change and global warming.
Sorry, Dr. Sherman, this is Denise. We only see the cover slide.
Oh, okay.
Yes. Okay, now it's okay.
Yeah, my slide has changed. Maybe a bit of a delay.
Okay. So now you see the Velders base slide showing the phase down of how the phase down of HFCs will reduce potential climate change by 2100.
Yes.
Okay. Okay. So can I move on to this slide? The next slide is okay. The next slide is the not so good news is that a low GWP MAC refrigerants are used in only a fraction of vehicles sold globally. The low GWP MAC refrigerants being primarily HFO1234YF or carbon dioxide. The solutions are needed for growing and emerging markets, especially in Asia and particularly in China and India, where the population is growing rapidly and standards of living are increasing rapidly. So this chart shows that how since 2013, there's a total of about 500 million vehicles on the road with mobile air conditioning using HFO 1234YF. Excuse me. Over 500 million vehicles on the road, period, with mobile AC since HFO 1234YF was introduced. The amount of cars using HFO 1234YF is only 65 to 85 million, according to Chemours, one of the major suppliers. So there's many of the cars on the road are still using HFC 134A. So what is a secondary loop MAC system? The image on the left, is everybody seeing this slide with the image of the two systems?
Yes, we are.
Yes, okay. The image on the left is the direct expansion system, which is used in most mobile air conditioners right now. And the image on the right is the secondary loop system. And you can see that the image on the right has a loop in green, a piping loop in green, and that's where the refrigerant would go. In the direct expansion system on the left, the refrigerant moves throughout those purple tubes, which means that they actually enter the passenger compartment. In the secondary loop system, the purple tubes carry coolant, which is non-flammable and can enter the passenger compartment without any risk to the passengers. So it also means that really any refrigerant can be used in a secondary loop system because the refrigerant stays only in the engine compartment. The secondary loop system also uses fewer fittings and shorter refrigerant hoses, so there's less chance of emissions of refrigerant. One of the key features about the secondary loop system is that you can see there's a purple tank on the right, in the image on the right, and that holds the coolant. And that's called thermal ballast because it retains coolness even when a vehicle stops for a short period of time. So for example, if someone is making deliveries or stopping for a quick errand, when they get back into the vehicle, it will cool down much faster than in a direct expansion system. Or if you have a stop-start vehicle, it will save fuel because the car won't have to turn on while the vehicle is stopped in order to run the compressor to keep the vehicle cool. So it's a efficiency savings and a fuel emission savings. Our demonstration used a Tata Aria 2.2L liter Dicor vehicle. It's a small utility vehicle that's shown on the right. And our goal was to show that the SLMAX system can reduce refrigerant emissions and maximize energy efficiency by using improved powertrain control logic. And the powertrain control logic is just the software that allows the powertrain and the air conditioning system to communicate. So it tells the air conditioning system when to turn on, when the compressor should turn on. So for example, the compressor can turn off when the vehicle is accelerating or going up a hill, which saves energy, and then it can turn back on to cool down the vehicle when the car is slowing down or going down a hill. So by maximizing that powertrain control logic, we get what's called enhanced air conditioning, and it takes maximum advantage of the motion of the vehicle to minimize fuel emissions and increase energy efficiency. Our partners, as has been said, are MAHLE, Tata Motors Limited, and IGSD, and dozens of collaborators and advisors. The refrigerants tested were HFC152A with a global warming potential of 138, and HFO1234YF with a global warming potential less than 1 in an SLMAX system versus HFC134A with a global warming potential of 1300 and HFO1234YF in a direct expansion system. And of course, we are very, very grateful, as said before, for funding from the CCAC. Okay, so this slide shows our core SLMAC demonstration team and our and advisors. Most of these were directly involved in the project. From TML, the lead was Sangeet Kapoor with Prasanna Nagarhali, and Jagbendra Meena was the lead engineer. From MAHLE, Timothy Craig was the lead, and Lindsay Lietzel and Dr. Saurav Chaudhuri were the engineers. Jim Baker was our consultant, and IGSD, we were led by Dr. Stephen Anderson and Melinda Soffer, and I participated with Kristen Tedonio. We also have this long list of advisors from Ford, GM, California Air Resources Board, universities, NRDC, a wide list of advisors and experts to help guide us along the way. And it wasn't just building the vehicle, it was also developing new standards with the Society of Automotive Engineers, doing a risk assessment update, doing a life cycle climate performance analysis, and just a very, very broad, comprehensive project. So why are SLMAX systems needed? As most of you know, HFC 134A is being phased out because of the Kigali Amendment. 1234YF is expensive, it's covered by patents. It risks recharge substitution with HFC 134A because of the high cost. And in India, where our project was based, about 25% of total HFC use is with MAX, and about 20% of the motor vehicle fuel used powers MAX. So HFCs are a very substantial factor in climate in India, and affordable, efficient, low GWP options are needed. So why not direct expansion with a low GWP refrigerant? Direct expansion limits your refrigerant choice. It has to be 134A, 1234YF, or carbon dioxide. 134A is being phased down, 1234YF is expensive, and CO2, which many are interested in, has very expensive components, has performance concerns at high ambient temperatures. So it's used in very, very limited areas right now, in very limited markets. Secondary loop widens the engineering options, many more and several more choices. We understand hydrocarbons are possibly being tested in secondary loop systems in the international market. And it allows for innovative engineering to maximize energy efficiency through use of the powertrain control system. And there's also savings potential for the consumer with fuel and air conditioning maintenance savings, and the manufacturer savings through refrigerant cost control, fewer leaks, fewer repairs under warranty. So a secondary loop system provides advantages with an R134A system, 1234YF, or 152A. All of these, you have fewer fittings and shorter hoses for lower leak rates, higher reliability and lower service cost. You have this capacity for cold storage and a quicker cool down after a quick stop, a smaller refrigerant charge. You have manufacturing savings versus a direct expansion 1234YF system in a car with two cooling points, front and back. There's less air conditioning system noise and vibration because of the shorter hoses and the fewer connections. There's lower life cycle TFA emissions, that's trifluoroacetic acid. It occurs in the environment, very small emissions with 1234YF, but 152A has no TFA emissions. There's a reduced likelihood of service recharge with 134A, extended stop-start, and improved life cycle climate performance versus direct expansion 134A systems. We included 152A in the test because it's more affordable, it works at a lower pressure, so it has higher efficiency and a high ambient temperature. There's more than a 95% reduction in direct refrigerant emissions impact due to the reduced charge and lower GWP, has good life cycle climate performance, no TFA, and importantly, it satisfies the US EPA Significant New Alternatives Program, or SNAP, and the EU F-gas Directive, which requires the GWP less than 150. So now I'll turn it over to Tim Craig and Dr. Chowdhury to talk about the system and some of the technical aspects of the secondary loop MAC program.
Okay, thank you, Nancy. Can you hear me all right?
I certainly can.
Okay, good. Well, this is Tim Craig, and I appreciate the opportunity to give an update to those on the line relative to the technical aspects of this project. I'll give a quick introduction, and then Saurabh Chowdhury, who is the principal investigator, will go through the technical details. So first, in addition, let me thank the other members of the project, certainly IGSD and also CCAC for funding this activity. I wanted to give a bit of perspective on this system relative to the applicability of secondary loop technology in the automotive environment. Because we are a supplier, we work very closely with the OEMs, and we look at various aspects of technology and the opportunity for an OEM to adopt that technology. In addition, secondary loop, when you look at it from multiple aspects that would be of a customer concern, it's applicable. First of all, if you think about complexity, although there are some additional components added, the relative level of complexity of a secondary loop is in what I would call the simple category relative to automotive technologies that can be implemented. Secondly, you sometimes look at readiness. Is a technology ready for implementation? This technology is ready. The components needed to apply it are all in the market today. So there is not a technical barrier in terms of readiness to use the technology. Then you look at the effort required to apply it, and this is in the category of what I would say is normal development. There are no special development techniques needed. There are some additional challenges around packaging additional parts and carrying some of the additional mass, but we believe that with this technology, the benefits outweigh those costs. The second aspect I wanted to just give an overview on before Saurabh begins discussing the technical details is energy efficiency, to give you a perspective on what that means. Nancy did a great job of talking about how we can integrate powertrain control with the cooling technology that's discussed here. And just as a food for thought, think about it. Is it possible to save more energy on a vehicle level than the AC system uses? That may seem counterintuitive to those on the line, but actually that's what we demonstrated. By appropriately using the powertrain controls with the ability to store cold energy, we were able to show that we can save more energy at a vehicle level than the AC system actually uses. So again, that may seem counterintuitive, but that's the beauty of innovation. So again, the advantage of this system is that we are able to store cold energy while the system is operating and take advantage of that stored energy to be able to turn off the compressor at appropriate times and match it with the powertrain demands to improve the fuel economy. So with that perspective, I'll turn it over to Saurabh Chowdhury to go through the technical details.
Thank you, Tim. I will go over the technical details, which are approximately, I think, slide 12 through slide 23. And then I will turn over to Nancy to finish the presentation.
Okay, Dr. Chowdhury, we're having a little trouble hearing you. Can you maybe get a little closer to the mic?
Sure. Can you hear me now better?
That is much better. Yeah.
Okay.
Thank you.
So the first slide, the technical slide, which is slide number 12, shows the Tata area SLMax bench testing setup. So we did this project in two phases. One is on the bench, which means a setup which is similar to the vehicle setup prepared on the bench and studied carefully with due instrumentation to understand the system capacity, the nuances of how the system works, and accordingly make changes to the system and components to improve it. And once the system is verified on the bench, we have taken those components back to the vehicle and implemented the system on the vehicle and tested the vehicle. So the first slide here shows that we started at a component level. We took the evaporator, which is cooling the air from the vehicle, and we tested that separately as one component. We also looked at the condenser from the vehicle, and this evaporator in our SLMax system is replaced by a chiller and a cooler combination. The pictures are shown for the chiller. The cooler looks very similar to an evaporator. This combination is tested separately as well. On a system bench, which is shown on the right side, we connected the different components, including the coolant loop, as it would be on the vehicle, with a similar line length and similar level of instrumentation. And we tested this at our Lockport, New York facility. Nancy, can you please move the slide to the next slide, 13? Okay, this shows the schematic of the test setup. The refrigeration system is shown on the top part of the sketch, which has a compressor which compresses the refrigerant, feeds into the condenser, which is shown by the orange rectangle. The condenser condenses the refrigerant, passes it to a TXV or a refrigerant valve, and that expands the refrigerant into a chiller. The chiller has another stream running through it, which is shown by the blue lines at the bottom part of the sketch. That is the coolant loop. The coolant goes through the chiller. The refrigerant on the other side cools the coolant, and the cold coolant is fed to two coolers. There are two coolers because the system on the Tata area has a front evaporator and a rear evaporator. Front evaporator is for the front driver and passenger climate control, and the rear evaporator is for the second and third row seats. So the coolant is fed to the coolers in those two locations. There is a reservoir which can accumulate the amount of coolant which is chilled by the chiller, and it can dispense it based on the requirement of the vehicle. As you will notice that on the top part, which is the refrigeration cycle, there are shown O-ring joints before and after the condenser, before and after the compressor, and at the TXV. These joints are where refrigerant from the system can leak out and cause global warming. So in this particular secondary loop system, we have reduced the number of joints compared to the direct system in the baseline vehicle significantly. And later on in the presentation, you will see the effect of reducing those number of joints and reducing the leakage as a result. Can we please have slide 14? In the slide 14, we see the two comparisons. One on the right is according to the SAE2727 standard. We have done calculations to show the baseline area system, direct system versus the SLMAC area system, what the difference is in R134A emissions in grams of refrigerant per year of usage. We have done this calculation with assumption that the compressor has a single lip seal versus it has a double lip seal. So you have on the left column, you have 1 and 2 showing those two variants. The baseline versus SLMAC shows significant reduction up to I think between 40 to 50% approximately reduction in refrigerant. This is just pure calculation based. On the left-hand side, the blue table shows the actual test which is conducted according to SAE J2763 standard. And there are two types of tests. One is a static test and one is a dynamic test. The difference is the static test is the refrigerant system is put into a chamber and we measure the amount of refrigerant gradually being leaked from the system into the chamber without the system being turned on. In the dynamic test, the same setup is turned on, and then after a while we measure the result of the emissions. And we are seeing that up to 60% reduction in refrigerant emission is observed on the SLMAX system with respect to the baseline system. So both by calculations, which is showing 40 to 50%, and by actual test measurement, which is showing up to 60%, we are reducing the amount of refrigerant emission of 134A. Next slide, please. So this chart summarizes the test results on the vehicle, which is performed first by MAHLE at our Lockport facility, and then the vehicle was transferred to Tata facility in Pune, India, and they performed these set of tests or measurements to assess how we are faring against the baseline vehicle. So of course we are using this low GWP refrigerant, which is one of the targets. By the way, the targets were set sometime in the early phase of the project after understanding the system behavior and the system requirements. Tata and MAHLE jointly set these targets to ensure that the progress of the project is in the right direction. So we are, by using the 152A and 134A refrigerant, 1234YF refrigerants, we have met the GWP reduction target. In our system, because we have a very compact system, which is shown on the upper part of the sketch that I referred to a couple of slides before, we are reducing the amount of refrigerant significantly. The baseline vehicle came with 800 grams of 134A refrigerant, and we reduced the amount of refrigerant to approximately 430 grams, which is amounting to approximately 46%. Target of 40% is met. The average cabin temperatures, there are two rows there. These are tests of actually how the AC system is cooling down the inside of the cabin in the vehicle. The criteria is at 25th minute at two different temperatures, 35 degrees centigrade and 45 degrees centigrade, which is very high temperature. We need to be at the baseline level, which is about 21.8 degrees centigrade and 28.9 degrees centigrade. So the baseline car gave those two types, those two numbers or temperatures at 25th minute into the test. When you start the car on and you gradually cool down the vehicle at the 25th minute, what is the internal average temperature in the cabin? The target is to meet the baseline basically. And we are seeing that with the 152A results, 23.8 degrees centigrade and 31.5 degrees centigrade are achieved by the system. Let me explain why we are exceeding the cooling target, or we are exceeding the temperature target. In our setup, when we observed what are the requirements to meet the baseline, we wanted to increase the compressor capacity because 152A system required that. However, the vehicle's mechanics and the design of the components are such that it could not accommodate a larger sized compressor. There is a physical limitation to that. We discussed with Tata engineers and we agreed that we will continue to use the baseline vehicle's compressor, which is smaller size than we need. And we will calculate at the end of the test what would be the requirement, what would be the result if we had a appropriately sized compressor. So the deficiency in cooling by approximately about a degree or 2 degrees that we are observing would be easily met if we had the appropriately sized compressor. The next couple of lines are related to the power consumption. As you see, the compressor power consumption in the baseline is 5.5 kilowatts at 2400 engine RPM. We wanted to reduce it by 5 to 8%, and in fact, our test at Tata has shown that 9.6% reduction, which is quite significant. Part of the reason why the reduction is there is because R152A, as Nancy mentioned earlier, has a lower operating pressure, and as a result, the compressor doesn't have to work as much in order to provide the cooling with 152A. The rise of grill temperature in city cycle tests, where we are actually switching the compressor off temporarily when we are at a traffic stop, we observe the grill temperature rise to be about 2 degrees centigrade. The target was approximately 2 degrees, and the baseline system, of course, had a much higher rise in temperature, showing that the baseline system cannot afford to have a compressor turned off, whereas the secondary loop system can afford to have that compressor turned off. The fuel economy on an Indian drive cycle, uh, which is basically the main reason why we wanted to do this project, is to improve the fuel economy. Apart from using the lower GWP refrigerant, we observed that we are getting about 1.9% to 2.6% in a mix of a city type traffic drive cycle and a highway type drive cycle. In a city cycle, we have a stop and go type traffic. You drive a little bit and you stop at a stoplight or at a traffic stop, and then you move on again. This type of driving behavior is not very efficient with respect to the miles you drive. On a highway drive cycle, you have a high speed driving and almost a constant speed for longer durations, and you have much less frequent stops. So we have to assess our benefits on both these type of cycles or driving routines. The target was 3%, and with the highway type of conditions, I think we are meeting that because we did a couple of tests. Our range of fuel economy calculation or measurements varied between approximately 1.9 to 2.6. I want to mention on this point a little bit more because this is a very important criteria for our customers. We implemented together with Tata, we implemented a logic when to turn the compressor off. This was fine-tuned after a couple of testing routines, and we observed that we are getting a fuel economy benefit right away without turning the engine off. Now, when we are at a traffic stop, we can very easily turn the engine off and get an even higher benefit in fuel economy. We could not implement that because the vehicle didn't have the capability to accept a start-stop of engine technology. So we just performed a start-stop of compressor part. So if you see the last bullet point in that lowest row, it says engine idle stop strategy will increase fuel economy. That is what we mean when we say that in a future vehicle, if we could implement this stopping of the engine during an idle condition or during a traffic stop, we would save even higher amount of energy. Nancy, kindly move to slide 16. This is our vehicle in testing phase when we have Tata engineering manager Prasanna Nagarhali visit us at Lockport, and we had demonstrated to him the progress of the project at that point. This is almost at the final phase in the project when we are wrapping up our final vehicle testing at Lockport facility. Right after this picture was taken, the very next day, we started the process of shipping this vehicle back to Pune, where they performed more detailed tests. Here we see Mr. Jagavendra, who is a technical expert at TML, and who came to observe the testing process and assist us with data analysis. This picture shows the Tata area vehicle, the one that we worked with, and an identical sister vehicle. These two vehicles were road tested in India in several locations, both on a city traffic as well as a highway type condition, and the fuel economy was measured from these tests. Um, this slide shows exactly what I was talking about relative to the compressor not being appropriately sized. The blue bars shows, the blue columns rather, shows um, the system's fuel economy if we move from the R152A secondary loop to R152A with a logic of compressor stopping during idles, and finally with R152A with compressor stopping as well as engine stopping. The engine stopping part is an estimation based on the fuel economy numbers that we arrived at or found from our testing. So following these blue bars progress, you can see that our fuel economy is slightly deficient based on the R134A baseline if we continuously run the compressor. If we introduce this logic, which we did on the vehicle, we are exceeding the R134A fuel economy by approximately 2%, 2.2%, which is quite significant in automotive world. And then going to this new logic, Nancy, can I finish off with the previous slide? With the new logic, we can see that we can achieve up to 9%. The red bars are if we appropriately size the compressor, we estimated those, and you can see that the progress is very similar. We can achieve up to 8% fuel economy improvement with the best logic applied. In the next slide, here we see the progression, how we get from our standard refrigerant 134A system. Right now, we see in most vehicles how we get to a very low GHG emission from max. The first step shows if we enhance the current system, just improving, for example, the hoses and the joints and the compressor type, we get a significant benefit waiting to happen, 44%. Then, if we have this vehicle and improve it with proper insulation, proper kind of glass which reflects most of the heat, we will get an additional 15% benefit. Finally, if we implement start-stop logic, we get another 4% benefit approximately. And with the new refrigerant 152A introduced, which requires less power from compressor, you get an additional 7%. So overall, we get approximately 95% benefit if we can walk through this process and implement it in all the vehicles. This is a similar chart as discussed before. Here we show the Indian drive cycle. If you see, the first city phase has frequent stops and starts, and the vehicle speed is relatively low. In the highway cycle, we have a high-speed driving. There are some decelerations and accelerations, but there are actually no stoppage of the vehicle in that phase. And we achieve the fuel economy, as I mentioned, with stopping the compressor as well as stopping the engine to conserve the fuel economy or the fuel usage. So this is overall what the project achieved. We reduced the amount of charge in the refrigerant system from about 800 to 430 grams, and we also improved the leakage by improving the joints and reducing the number of joints from about 37 to about 59%. And finally, as I mentioned, by walking through these different steps in technology improvement, we can reduce the total GHG emission by 95%. I think this is the final picture after the vehicle project ended. This is in about February 2018. And in the middle of the picture, our beloved Dr. Stephen Anderson shows in the picture where he actually visited the facility and observed the final testing process. Nancy,
Okay.
please take over this slide.
Yes, so I'll take over, and the figures for these slides were produced and calculated by Kristen Tedonio, who I think is on the line, but it shows the projected secondary loop manufacturing and ownership cost for India for a 2 cooling point system, cost and savings in US dollars. So in terms of the refrigerant, the charge in a direct expansion system with 134A is 800 grams. With 1234YF, it's 750 grams. And for secondary loop system, it's almost half at 430 grams. So the CO2 equivalent tons for the initial charge is 1.04 for 134A, but less than 0.01 for 1234YF and less than 0.1 for 152A. The added manufacturing costs baseline is the R134A system. There's additional costs for 1234YF, and that includes both the components and the cost of the refrigerant, and increase of $36 for 152A, again, including the extra components and the refrigerant charge, as well as the reduced cost for the refrigerant. The service cost, it's estimated that there would be fewer services with the secondary loop system. So it's $57 every 3 to 5 years for 134A. For 1234YF, it's $133 every 3 to 5 years. And for secondary loop system with fewer services, it's $54 every 6 to 10 years. So the annual fuel savings for the secondary loop system would be up to 37 liters at $37 at $1 per liter, and a savings of 1 ton of CO2 equivalent over 10 years. So in summary, there are original equipment manufacturer savings, owner savings, service, and citizen benefits. For OEMs, there's a lower refrigerant cost with multiple suppliers, higher reliability, it's a more environmentally responsible product, has potential for MAC credits. For owners, there's higher reliability, lower service costs, and fuel savings. Service shops and technicians have the advantage of the secondary loop system makes do-it-yourself servicing less attractive. And for the community, it's cleaner air and less climate forcing. So in terms of communications, the project has been widely publicized since its beginning in July 2016. There have been 14 papers and presentations by the entire team, members of the team since July 26. Audiences have been Montreal Protocol meetings, industry, and public audiences. In addition to the IGSD reports, there have been milestone reports submitted by MAHLE and Tata Motors according to schedule, including their very, very substantial final reports. 11 meetings and side events have been conducted or attended to present the project progress and the results. And there's been coverage in more than 20 mainstream and industry media as a result of the press releases and papers, including Reuters, Economic Times, and Automotive Engineering Magazine. And this slide just gives a portion, not entirely complete, because they don't fit, of the presentations and papers that have been given on the project, including a 2019 presentation at the SAE, Society of Automotive Engineers World Congress, just this past spring by Kristen and Tim. So the bottom line question is, how will the Kigali Amendment affect mobile air conditioner engineering? And the answer is that the amendment will accelerate the transition away from 134A. Solutions are urgently needed in emerging and growing markets, which are very price sensitive. The traditional direct expansion design has drawbacks that limit refrigerant choices. Electric vehicles are now looking at MAC innovation, and new designs such as secondary loop engineering allow options and engineering solutions that can improve fuel economy and reduce greenhouse gas emissions. So thank you for listening. We really appreciate your attention, and now we'd be happy to take any questions you might have.
Thanks, Nancy. So right now, everyone is muted or are in listen-only mode. But if you can click the raise hand button that's located in the control panel, I will be able to unmute you. So when you ask your question, please don't forget to introduce yourself, including your country and your organization. Okay, we have a question from Mr. Gabriel Hoffman. So I'm going to unmute you. You have the floor. Mr. Hoffman from Germany, can you unmute yourself if you're muted? You can ask your question now. Sorry, Miss Gabrielle. Yeah, we can hear you, but not very loudly. If you can speak closer to the microphone.
Troy, is that better?
We cannot hear you very well.
Maybe I can write my question.
Yes, if you can write your question, that will be helpful. We can hear you, but it's very faint right now. So you can also write your question in the chat box. Okay. So I'm still looking at if you can raise your hand using the control panel, that would be helpful. Meanwhile, while you're trying to figure that out or maybe typing your question, I had a question for Mr. Timothy and Mr. Sorav. In terms of like the future, what are your plans moving forward now that we have this technology tested? This might be interesting for many of the participants.
Yes, thanks, Denise. There's, first of all, the ability for OEMs to apply this is ready today for future vehicles, and they typically take 2 to 3 years to develop. So the components are ready, and we're willing and anxious to work with any OEMs that are interested. The second main activity that is still underway and needs to be completed before it's used commercially is getting the standards updated so that the appropriate design aspects of the system can be applied. The standards I'm referring to have been used for many, many years as guidelines for the safe application of technology in mobile air conditioning systems. So along with Kristen Tedonio and others, we are working with the SAE committee to establish those standards. They will probably take some months to complete, but essentially our plan is to continue to market this to our OEM customers and to support them in development, as well as complete those standards that I mentioned.
Okay, that's very helpful. The question from Ms. Hoffman was, did you try or calculate with hydrocarbons? And do you also include hydrocarbons in the standards?
We did not use hydrocarbons in this particular case, and we did not calculate with those. They are really in the early stages of evaluation right now. One of the key elements that has been accomplished for all the refrigerants that Nancy mentioned that are compliant with the EU directive and also approved by the U.S. EPA is that they have had risk assessments completed to show that they can be appropriately applied in mobile air conditioning environment without additional risk to any user or passenger. So one of the key elements that needs to be completed relative to hydrocarbons is to clearly understand the size of the refrigerant charge that's needed, and then evaluate any potential risks that would come from that. So that work is underway in various communities throughout the world, actually, and we're monitoring that and assisting where needed.
And Denise, this is Nancy.
Mm-hmm. Go ahead.
If I could just answer your question about the future, some of the ideas we've discussed about the future and that make a lot of sense would be to first to scale up the project, to try using the SLMAX system on a fleet of vehicles, and especially trucks or delivery vehicles. Delivery vehicles like vans that make a lot of stops, where the secondary loop's ability to store coolness would be especially helpful. Or also at trucks, either small or large trucks, where there's more room under the hood for a secondary loop max system. It makes perfect sense to try installing and testing this system, and especially in a price-sensitive market where like a truck market, where they might be wanting to shave off every penny from their operating costs. They might be very interested in 152A. But again, the standards do need to be set for that.
Yeah, and one follow-up, Denise, quickly. I think we recognize that part of CCAC's objectives and mission is to reduce or phase down the use of HFCs, and of course we focused on using an HFC here, but our goal all along was to get the lowest carbon solution we could, to have an economic solution for the growing application of air conditioning in vehicles. So that's why we've continued to focus on the use of R152A. It's a very efficient refrigerant and helps in giving us the lowest carbon solution of those approved refrigerants, and that's why even though the HFC phase down is a goal, it's a good solution in this particular application.
Yes, thank you very much for your responses. And indeed, I would also assume that for many governments, fuel efficiency is quite important. So it was very interesting how you looked at fuel efficiency. And when you're selling this to the OEMs, I think they will be particularly interested in the data that you had collected on that. So we have a few more minutes for maybe a last question, if anybody is interested in raising their hands. Okay, we have other questions from the floor. I think the others have to disconnect because of the time limitations. So I would just want to inform everyone who are on the line that if you have additional questions, please feel free to send an email to the CCAC Secretariat. You also have my direct email that was circulated or sent through the webinar registration link. So we're happy to respond to any additional questions you may have in writing. So I think at this point, if it's okay, I would like to ask maybe our panelists to give some final words.
Tim and Saurav?
Sure. Well, first of all, again, I appreciate the opportunity to demonstrate the enormous potential that this technology has. It's an exciting future in the air conditioning environment to not only provide all the benefits for comfort and fuel economy, as well as driver alertness that come from using air conditioning, but do it in a fuel efficient and minimum carbon footprint environment. So we look forward to working with OEMs and those interested in applying the secondary loop system and using R152A as a refrigerant. So thanks again for your time and everyone's participation.
And I would like to echo Tim's thanks to everyone for their interest and for participating. We would be delighted to answer any questions that you may think of later. And I'd especially like to thank CCAC for the funding, and also especially to thank MAHLE and TML, not here, for the incredible amount of work that went into this project, and their dedication and seriousness and the commitment to a better climate for all of us. This presentation doesn't begin to show how much work is behind these few slides.
All right. Thanks everyone. Just a few questions I received as well in terms of sharing the presentation. Yes, those that participated and registered will receive the presentation as well as the link to the recording of this webinar. And I'd also like to point out that in the control panel, there's a section on handouts, and there you can find the final technical report of the project, and there will be more details as well in terms of the results. Again, thank you so much to our distinguished panelists and speakers. Thank you so much to IGSD, to MAHLE, and to Tata, who couldn't be here but has been an instrumental partner in the implementation of this project. Thank you very much, everyone. The webinar has now been concluded.
Thank you, Denise.
Thank you.
Thank you.
Bye, everyone.
Bye.